This is chapter 5. Specifically, we're going to talk about 5.1 work. So today you'll learn how to calculate work. We'll talk about that angle between work and distance and describe the difference between work on versus work done by. There are several different types of forms of energy. One of them is mechanical, which is what we're really going to focus on. We have a couple of different types of energy in mechanical, such as kinetic, which is just motion, and potential, which our potential won't be like stored potential energy, like when you eat something. What we're going to talk about as stored potential energy will be more with position.
So like a ball that you're holding in the air versus a ball on the ground.
Correct. That's what kind of potential there is. There are other types of energy, such as chemical, which is the one where you eat and it gets stored in your body, and also like a battery. Those are chemical. And then we have electromagnetic, and we also have nuclear. So we're not going to get too much into these. We'll touch a little bit on electromagnetic energy, just a little bit, but the other two we will not be talking about very much. Not how to calculate it, at least. Okay, so there's some things that we need to look at with energy. One of them is that energy can be transformed from one version to another version. The total amount of energy never really changes, though. Not never really, it just never changes. There's some infinite amount of energy, or some finite amount of energy in the universe, and it's always transferred from one form to another. We can use energy instead of Newton's laws, all those F equals ma and stuff like that. We can use energy to kind of make them more simple. So here's the equation for work. Now, work is a transfer of energy. It's not necessarily a type of energy. It's like one type of energy turning into another type of energy. And for that to happen, energy has to be transferred. And so we call that work. Yes.
So it's just kind of like work isn't in itself an energy?
Correct.
It's just the bridge?
Yes.
Okay.
So for instance, you can imagine you're a peasant and you're working out in the fields and you're converting your energy into pulling up weeds or whatever it is in the farm. And so what you're doing is you're transferring your energy into that motion of picking up the weeds, and that's work that you're being paid for.
Well, if you're a peasant, you're not really being paid.
Peasants gets paid.
No.
Yes, they do.
Slaves don't get paid. Maybe you're a slave.
Indentured servants don't get paid either, but they work off their reps.
So you can imagine that work, just like work here, when we work, we get paid for things. Work is a transfer of our energy into doing something productive, and we get paid for that. So you're getting paid for the energy that you're outputting. Work is measured in joules. You haven't seen joules before. I can tell you that joules is newtons times meters, because this is newtons and this is meters. Distance is meters. A lot of times you'll see this as force delta x, but it'll be, instead of delta x, cosine will be force dot delta x. And that's where that cosine kind of replaces that. But we're just going to use this equation, force times distance, cosine theta. And that theta is special. It's not the proper angle theta, it's the alligator angle theta. It is, for instance, we have some sort of force that's being applied to a box, let's say like that. There's our force. And if our box is moving this direction with that some sort of distance, the angle between the distance and the force, that's the theta we're talking about. So if we're talking about force going that way and distance going that way, it's this angle. It's not the proper angle.
Wait, so...
It is not this angle. It's not that.
So...
It is only the angle between force and distance.
So if you have distance being, out to the right,
Mm-hmm.
and then force, that's like, say, 20 degrees below it,
Mm-hmm.
then it would just be negative 20, not...
It'd just be 20.
Oh, it would just be 20?
You don't have to put the negative
Not,
in. It's the alligator angle,
you know,
not the
340.
proper angle, not this one.
Okay.
Just the angle between them. So if the angle's this way, the angle's this way, the angle's this way, the angle's super big, That's all it is.
Also, that makes really cool notes when you write.
It does.
Yeah, kind of.
It drives some people crazy. I don't think it's Sonic. Is
It
it?
is.
Is it
Based
Sonic?
on, I mean, I don't have a whole lot of experience with it, but just from listening to it, it probably is, I think.
Maybe.
Well, I mean, it would make sound based on, well, I mean, it perceives the sounds.
Define Sonic.
Well, I mean,
Sound.
Sonic, like,
Sound?
It runs on an ultrasound somehow.
Oh, it could. It could run on ultrasound, maybe.
I think somehow there's like phase difference or something.
sounds fun.
Maybe. Okay, so work in general. Force and distance are in the same direction and the angle between them. So for instance, here we have displacement and we have force. They're in the exact same direction, so the angle between them is going to be 0. If they are at some sort of angle, like this, then you can see that that force is doing work on the box only partially. So some of the work is wasted in the y direction, but a lot of it is causing it to move to the right. Think of it as a transfer of energy. This is the most transfer of energy. All the force is exerting, you're most effective in that direction. The energy is being transferred in order to move it. In this case, only the amount of energy that you're using in the x direction is actually causing it to move. This upwards force is being wasted, so you're wasting a little bit of your force. So the only amount of work that you're doing on the box is only the part that's causing it in the x direction. So if you have a force in the y direction and it's moving in the x direction, you're not actually doing any work on the bucket with that force. You're not actually transferring any energy into the bucket by carrying it sideways if you're lifting it up. The only work that you would actually be doing is if you were lifting the bucket. So in this case, whenever you have a 90, right, cosine 90 is 0. So the work done by that particular force would be 0. Which is weird, but there's a lot more movement that goes into carrying a bucket, right? You have to move forward, and your feet are causing forces against the ground, so your feet are actually doing more work. In that case, they're actually the ones that's transferring the bucket into moving forward, because they're in the x direction. You're like fighting friction to move forward. I'm going to get the cups. Hard to read your guys' face. Okay, so when there are multiple forces acting on the work, we can do two different things. You can find the work that each does separately, so you can find the work of this force versus this force versus this force, and then add up all the work. Or you can find the net force first and then find the work. So you can add up all the work, or you can add up all the forces and then find work. This just looks so delicious. I want to eat it. With the pretty blue color.
Well,
Like blueberry Jolly Rancher.
Are you like
That's
the
what I
3-year-olds who they tell parents to keep things out of reach?
Well, I just don't know why they have to make it such a pretty color. It just looks so tasty.
Really, they shouldn't make things colorful.
They shouldn't. It's bad.
What is more appealing? Your senses then.
It is.
Yes, which
It's
is
more
bad for
appealing to
children.
taste.
What I'm saying is they shouldn't make things like this pretty.
Like
It
it's
should
food.
be like clear. I don't want to eat
does
this.
significantly look
I
like
want to eat
costume.
this.
Like if it's food, yeah, sure, make it pretty if you want. But if it's not food, don't make it pretty. Right.
Okay. We're almost finished. No, not yet. Okay, so work can be positive or negative. If it's positive, work has gone into the system. If it's negative, it's being transferred out of the system. Now, it's going to be positive if the force and the displacement are in the same direction. So, for instance, if this person lifts this box, the force that he's using to lift it is in the same direction in which the box is lifting. So he has done positive work on the box. Now, in this case, gravity versus the displacement would be negative because it's 180. They're in opposite directions. You're going to end up cosine 180 gives you a negative. So that one is going to be taking energy from the box. Negative 4.
So, okay, like when acceleration is negative but velocity is positive,
And it's
that's
slowing down.
right. So that would mean that negative work is being done, or
Well, if we're thinking about it in terms of acceleration, you got to turn it more into force. Like, what is the force that's causing that acceleration?
okay.
So the force, every acceleration is caused by a force, F equals ma. So you just take your mass times your acceleration. In that case, yes, it's slowing down. In that case, it'd probably be friction. If you have something in the positive direction with acceleration in the opposite direction, friction is taking the energy out of it. And that energy is transferred from moving energy, kinetic, into frictional, which is heat. So it's actually taking it and turning it into heat and sound and if fast enough light. Because that force certainly wouldn't be adding energy to it, right? If it's slowing down. Okay, anybody need more time with this slide? Work done by friction. Since friction always acts in the opposite direction in which the object is moving, then work due to friction will always be negative. So if you move this way, friction is always opposite. So it's always taking energy from the system. And as I just said, it is turned into heat and sound. So like you can hear papers moving against each other. And if I did it for a long enough time or fast enough, you're going to actually feel some heat. So my movement of my hand, I'm taking chemical energy, transferring it into kinetic energy, and then that kinetic energy, some of it's being lost through the sound and through the heat because of friction. You can also do this, and you can kinetic energy, your chemical energy into kinetic energy, which creates heat in your hand, and you can hear it. Especially if your hands are all dry and scratchy like mine. So here's an example of work for you before we get into our clicker questions. We have a 40 kilogram box. I'm going to write that down. 40 kilograms. What's that? What is mass? M. It's pushed across the ground a distance of 10 meters. What's this 10 meters? Displacement. We'll go delta x, or if you want to, you can call it d for now. A force of 20 newtons. What's this? Force F. Acts at 25 degrees below the horizontal. Yes, this is theta. The coefficient of kinetic friction between the ground and the box is 0.1. So what's 0.1?
Mu.
Mu. And it's moving, right? So it's mu k, if you want to be specific. A, what is the work done by gravity?
Gravity doesn't do work done.
Actually,
In this situation.
doesn't it affect the frictional force, however?
Yeah, but that's not that's force.
Okay, so we're going to draw a picture.
Force that you turn.
As you guys are discussing this, it sounds good to me. Okay, we have a picture. We have a force of 20 newtons acting at 25 degrees below the horizontal. 25 degrees. Force applied, if you want to call it that. We have the normal force, because it's sliding across the table, ground, whatever. It's got some sort of weight since it's an object, and it has some sort of frictional force. It is going this direction. So if you want to, you could actually go, that's like your delta x. You can ignore this stuff. There we are. Okay.
Racer's Sonic.
Yep.
Well, it would have to be.
Because it has to tell when. Yep, we're looking good still.
Oh, that's cool.
Oh, that actually works.
All right, let's do this. Go to that and that. All right. A. Work done by gravity. Call it WG. If it's remember, work is think that's above my here. Work is FD cosine theta. So this would be force, which is going to be
Zero.
the weight, mg, the distance, d or delta x, cosine, and 90 degrees, giving you
The
zero.
top part of that is being like cut off.
That's okay. You guys will figure it out. All right, B.
Okay.
What is the work done by the normal force? So F, normal force, work of the normal force, the Fn, delta x, or d, if you will, cosine, and that's also 90 degrees, right? 90, 90, and we're looking at, x because it's moving that direction.
Well, no, the cosine of normal force would be 25,
Nope,
wouldn't it?
nope, distance, that way. Right?
Oh, then it
Normal
would be
force is
cosine of 0.
90, so cosine of 90, the angle between them. X is that way,
Oh,
normal force is up,
that
90.
when it goes up and down.
Okay. C. What is the work done by friction? Work done by friction is going to be the frictional force, delta x cosine, what? We're moving that way.
So it's
And
the other
that's that way.
direction.
So it'd be
Negative 180.
So we're going to clarify this a little bit. This is actually mu Fn, delta x cosine 180. And this Fn in this case is just going to be a little bit more confusing since I have this down here in this direction. So we have to look back at some of the forces in we're looking for y direction, AY. We have Fn up, mg down, and some x or y component of this. And it's going to be down, so it would be like mg sine 25 equals, and then AY will be 0, so it should be 0. Are we okay with that? That's just the x component of this, or the y component of this weird angle, because we're pushing down on a little bit as we're going forward, like a cart. You're kind of leaning on the cart a little bit as you're moving, like a grocery cart. So in this case, sorry, I don't know what this mg sine theta is. This should be f sine theta, f applied. There we go. So Fn basically is going to equal the weight of the box plus the y component of whatever we're leaning on it with. This ends up being 49.8 plus 20 sine 25. $400. Okay, let's plug that into our equation over here. We have mu is 0.1. This is 400. The distance that it goes was 10 meters, and this is -1. So 0.1 times 400 times 10 should end up being 400. So the work done is 400 joules. Negative 400 joules. Thank you. And D. What's the work done by the applied force? So work done by our applied force, I'll call it Y. This will be applied force times the distance, cosine, and then we'll put that 25 degrees in. So this is going to be
180.
20. D is going to be 10. Cosine 25. And that should be 181 joules. All right, and then it says what's the net work done on the system? So the net work is just adding up all the works. So you're going to have 0 plus 0 plus 181 minus 400. So you just end up, wow, well in this case it's not going to work at all.
Yeah, I shouldn't have been able to overcome that much frictional force.
Oops. So this problem says that it should be going backwards
Due to
with
frictional
a
force.
work of 219. So the cart is pushing magically back on you by itself. The friction is so high that it pushes back.
That's pretty awesome.
You're getting mowed over by the
Shopping
cart.
cart.
So to fix this, I could do the frictional force is probably 0.01 instead. That would give us
Push it
40,
on, or push it back.
and that would make it a little bit better.
So 141 would be the network.
And that would mean it would actually work. So when you make your problems, make sure you don't suck at it like I do. Okay, and that would be the network on the system. That would be easy. Just gotta go and change that. So how do you feel about work so far? Should be pretty easy.
Seems like pretty easy.
This is like probably the hardest type of question you'll have to answer maybe. Okay, question 1. Rupel pushes a box 5 meters by applying a 25 Newton horizontal force. What work does she do? Her name is Rupel and she's a girl. Okay.
Maybe it's like some kind of weird swimming, like group show. Or Raphael.
You guys are so well trained, you put your clickers away.
Jump the gun a little bit.
This should be pretty easy.
I don't get this.
You don't get it?
No, I don't.
What part? The whole thing. Okay, the force, how about, well, let's just stick with the question for now. The question says that the force is 25 newtons and the distance is 5 meters. So if you just look at the equation, work equals force FD cosine theta, what would the answer be? Like, what would you plug into that equation?
They're in the same direction.
And they are in the same direction, right? I'm just pushing horizontally, 25 newtons.
Or ignore the cosine part.
Yeah, you could even do that. I mean, they're in the same direction, so this is still 0. But all I did for these is the force, which was for weight, is mg, the distance, cosine, and then it's 90 degrees, the distance, like basically the angle between here and here. And then for the normal force, it's just the normal force, d, which the distance is this way, and then the angle between them. So d is this way, normal force is this way, so I have yet again another 90. Okay, in this one, our frictional force is this way, our distance is this way, so it's 180 degrees. This frictional force is caused by the frictional force times the displacement, and frictional force is made of mu Fn. So now we have to go find mu Fn. And Fn is a little bit difficult, so we went back to last chapter. Here's F equals ma again in the y direction. In the y direction we have Fn, mg, and some component, because this one's kind of both in the x and y direction. So I took the y component of it, and then it's not moving up or down, it's just sliding across the surface this way. So our acceleration was 0, and then I solved for Fn. Once I had that, I can plug it into here and then put in all the other numbers that we were given. So that's how we got the 40 joules. Originally 400. Pretend it says 40. And then here is the applied force. This is pretty much what it's talking about here. The work of the applied force is the applied force times the distance it went times cosine 25. It's cosine 25 because the displacement is that way and the force is this way. So the angle between them is 25 degrees. Does that help a little bit better? A little bit. Again, this stuff is practice. If you're probably not going to get it until after you've done the homework and asked your questions and failed on them completely. So take a picture of the answers.
I did.
Good. And so when you do the homework, then you can check your answers at home and try to figure out why you did it. So when you come here, your answers or your questions are more defined. Because I can't like reteach the material every day.
Can I do that now?
Hmm?
Can you do that now?
Okay, so we have answers for this. Almost. Remember, FD cosine theta. F is this way. D is this way. So we shouldn't have an angle between them. We should just multiply them. Okay. So in this case, FD cosine theta, F is 25, D is 5, cosine 0 degrees gives you just 25 times 5, giving you 125 joules. Okay, question 2. A worker pushes a sled with a force of 40 newtons over a level distance of 6 meters. If a frictional force of 24 newtons acts on the wheelbarrow in a direction opposite of that of the worker, what net work is done on the wheelbarrow? You can either find the net work done by each force and then add it together, or you can find the net force and then the net work. If it helps, draw a picture. Sorry, We'll start the question. Should work now. They're probably going to ring the bell early for mathematics show, so we'll make this our last question and put your clickers away after you've answered. They're letting people out now.